All right. How's the project? Any issues so far? Let's see. I asked the TA to have a review session. Did you have it? No? Okay. So probably he's grading the second assignment, and maybe once he releases it, you could have the review session for both of them. But I will push for that to have it really this week or early next week for both assignments. Okay. Before moving to the third assignment, I really want all of you to get the feedback to know where are the things went wrong, where's a good side of it, and so on. Okay. Likewise for the project assignment, we're going to have the second assignment soon. It should be related to all those Boolean algebra. Okay. And probably we'll be focusing on sum of product of sums. Okay, how you get an equation or a problem that you describe as input to your program. Okay. All right. We still recording. Yeah, last time I forgot to mute the phone over there. So there was an echo in the recording. I tried to fix this using some software, some AI. It takes a lot of time. So it's crazy with the recording. Those a lot of efforts you don't see. They are happening really offline, but hopefully for your benefit. That's why I was a bit late in the recording, but now you have lecture 10 already online on YouTube. So we're missing only 11. Okay. All right. And for this guy, I'm waiting for the second in-class assignment. Once I get the grade, you'll start getting the alerts. We discussed this last time. By the way, let's take attendance for today. Please have a paper. Oh, yeah. Yeah. Any volunteer have a paper with name, student ID, please? All right. We're still in this beautiful book, very comprehensive, very nice book, very nice resource for all of you. We are in chapter 2. We are almost in the middle of chapter 2. We are still in the logic level, logic layer in the compute stack. And this is something nice. We'll stay with you throughout the entire semester. So please pay attention to that. You could print it and have it handy. So whenever we discuss any simplification, you can go directly to the table and discuss it. We are going to show it on the slide very often today. And for the De Morgan theorem, it's extremely easy, extremely straightforward. The only trouble with it is how to consider the right side, the left side of the equation. And you'll see a bit of tricks for today on the De Morgan. Hopefully we'll cover it today. Last time we discussed 5 examples. Each of them has its own trick, its own way how to start simplifying. And you saw last time, we spent a lot of time, but that is hopefully to discuss it gradually, how you would think about any equation. And you saw last time that there was no single way to solve the question. Sometimes we discussed like 5 different ways, right? And all of them will arrive to the same conclusion, same answer, but using different number of steps. Some of them very simple, using one theorem. Some of them really require you to go through several of those theorems. So this one was the easiest. Just take B as a common or use 3 theorems in order to solve it. And this one was a bit tricky because we have now 3 terms and we'd like to simplify 3 of them at the same time. So we would like to create another term in order to consider every 2 alone and then try to simplify them. And we said we could replicate or duplicate any of them without affecting the correctness of the equation, because any term added to itself is same as if you have only one of those terms, right? So ABC plus ABC is the same as ABC. right? So that's why we duplicate it twice, and then we can consider both of them together, try to simplify, take what is common in those terms, and then consider those together. We went through more theorem that we extracted from the original theorems, and we tried to prove them. We used several methods. Then, for example, 3 was a bit easy, but starting introducing you on how you can solve an equation when you have something multiplied by other equation. So you need to really to solve this one first, and then you can continue, or you can multiply the a with the term, a with the other term, and then you continue simplifying. Both ways can arrive to the same conclusion. Okay? But normally we recommend like try to solve this complex thing first. Try to multiply this over this over this, and then continue, unless this one is really large number of terms. If it is like 3 or 4, then things will be a bit more difficult, as we saw in example number 5. We're going to visit it now. For this one, straightforward, right? Since you already have a bar, so you can take a bar as common, and then plus 1. Anything plus 1 is 1, right? So you can cancel it out. Or remember our weird theorem? We covered it several times. Can anyone of you remind me what is the weird theorem? A plus B times C. A plus B. A plus C. Excellent. What's your name? Jordan. Excellent. This is what we call weird theorem, and hopefully you remember this throughout the entire semester. You will use it very often, and most of the question will be around this theorem, okay? Because it's really weird. We discussed last time, this is similar to say 3 plus, I'm going to use the exact same number I used last time, 8 times 5. In algebra, how we would solve this is we need to resolve the multiplication or the division first, because multiplication or division have the highest priority, right? And then we do the addition. But what's this telling us is that you can do something like this. Okay? Which is a bit weird. That's why we call it the weird theorem. Okay, so we cannot do this in Boolean, normal Boolean. We have to really solve this first and then add it to 3. What this is telling us is that we can distribute the 3 and the plus to this first, and then distribute again to this, which will result in this. Right? So if we want to solve this using this weird theorem, what we do, last time we discussed it several times, so hopefully it will be a quick one. Can anyone tell us how to use this for the simplifying this equation? So first,
Professor, could you move your camera?
Literal is added to the multiplication, right? So we have the a bar, right, added to this a bar BC, right? So the literal for that was, instead of a, we have a bar. So let's reorganize it, reorder it in order to be clear for us. We have this shape, a bar, plus, and then something with a multiplication. Now, in this theorem, we have 2, right? We have 2 literals multiplied by each other. And then you distribute the a over these 2. Here we don't have 2, we have 3. What should we do? Take a bar common. Yeah, this is one of the ways to solve it, but we don't want to do that. We want to go with this theorem, right? Now, we want to have those 3 literals in the form of 2. What should we do? A bar and...
Hi, Professor. Could you move your camera? Professor, could you move your
Hi.
camera? I can't see the whiteboard. Yeah, could you move your camera to the whiteboard? Thank you.
Can you see now?
Oh, yeah, yes. Thank you. Thank you so much.
It's a bit flipped.
Yeah, thank you.
But I don't know if you can see.
Yeah,
So
I can see now.
our right side is left in your screen.
Yeah, thank you. Thank you.
All right. Yeah, that's excellent point. So what we would do, we need to consider one of them as one literal and everything else as another literal. Okay? So you decided like you want an A bar to be one side and BC to be the other side, right? Excellent. So you can think about it as either you could assume like I want a Z, for example, equal BC, okay? And then this would be A bar plus A bar Z, right? And then you can continue from there, which would result in, I don't know if you can see on Zoom, it would result in, so you need to distribute this part over this and distribute it again over that. So that would be A bar plus A bar plus Z, right? And now you can replace back the Z with BC, and then you clear all the confusion. Or you can skip this step and just say, whatever you want, place a divider, and just distribute this over one side, and then distribute over the other side. It, again, doesn't matter if you place the divider here, here is exactly the same thing, okay? Yes, please. No. You have to really apply the theorem as is. As is. Please don't invent your own theorem. Okay? If the theorem says you have two sides, two literal, then please follow that. But you can always play around, same as we did over here. These are 3 or 4, 5, 6. How you need to divide them over 2. We will see this again in another example. So this is extremely important. All right? Now let's go to example 5. This was a bit tricky as well, but exact same idea as we did over here. So in this example, do you remember what we did? A as common. A as common. No. Excellent. So we said what we have on slide, it's exactly same as this form. It's exactly same as this form, right? So we have something as a sum of literals multiplied by another sum of literals, which is similar to this. However, exact same story. Here we have one plus another, and one literal plus another, right? Now, how to make that to be similar to this shape? We need to have something as one literal added to another. But remember, in this theorem, we need to have the same literal placed in both of them. If we don't have it, we cannot apply it. Do we have something common between the two parentheses? That is A. Excellent. Now, because A is common in both of them, and we have this shape, then we could convert it back into that. And that will be sum of products. So now let's take the A common. Let's take the A common. So we're taking A and plus back, same as we did over here, A plus. So we take it from both parentheses. Now, from the first side, what is left? C plus D plus E, right? The other side, just B. Now, don't forget about the multiplication. This is multiplication, not add. Why? Because this is what we have over here. So we consider the entire thing here as one literal, okay? And this is another literal, and that will be exactly same as this shape. You could, if you get confused by this, you could assume before. I want to assume like, we have x? No. X equal c plus d plus e, and then rewrite this to be this using x, which will be a plus x, a plus b. And now it's a bit easier for you to match this with what we have in here. And then easier for you to go back in this shape. Once you get this, what we do, for example, or you can use the other method that we used last time. For example, instead of trying to simplify, you could multiply a with with c, a with d, a with e, and then b with this, b with this, b with this, until you get very long equation, and then you try to simplify. Okay? All right. So now this is a new example. Everything before, we already covered it last time, right? So hopefully you are practicing, you are using the book to visit all those examples. You have a lot of questions at the end of the chapter and the section. Please go over that and try to solve them. If you have any issue understanding any of them, please ask me after the class, or visit me in my office, or send me an email and we can discuss it. All right. Do you remember the table of theorem, or you want me to go over it again? You can do the same here, write it here, and then we go with the table. So this is a, b plus bc plus b bar, d bar plus a, d bar, d bar. Now let's go back to the table. I'm not sure if Zihan can see this. Yeah, anyway. Yes.
Do you have a problem like break them?
Definitely, definitely. Okay, this is one of the trivials. Again, here we're covering just T6 to T11, right? And there is T12, which is De Morgan, but there are other theorems before this, and there is another table for the trivials, right? This is among the trivials that you can split this into two terms, right? And take different parentheses that you add them. For example, I want to consider those together. So you can just add parentheses over here. But don't place the parentheses after the plus. That will change the formula, right? So if you place a parentheses over here, then that will cause this to be multiplied by that, which is not true. So this is from algebra, right? It's exactly the same thing. Only we have one weird situation is the theorem we explained over here. That's why we call it weird theorem, okay? Everything else is exactly same as algebra. If you would do that in algebra, then it's permissible to do it over here, okay? The last time we said, whenever we saw a NOT gate, like the bars, then it's a bit easy for us, okay? Why? Because we would think about something we would take in common that would result in having something like A plus A bar. If we have this situation, that's amazing, because directly this would result in 1, and then it will be canceled out, okay? Or the other situation, we would have something like 1 plus something. Now this doesn't matter. It could be A, it could be A bar. Exact same story. Anything added to 1 is exactly 1. Anything added to itself with a NOT then it's also 1. And if you, again, cannot believe it, just try it with different values for truth table. Okay? Now, how it go with this into any of those two situations, if it is allowed, or using any of those theorem to move ahead. Let's see. Do we have a nut? Yes. Where is it? Here, 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 there. Okay. Now, can we take a common between any two terms such that we have in one side with a nut and another side without a nut, such that we can get this situation or this situation? Let's see. For example, here we have B bar, here we have B, which is great, but we cannot take anything common between these two. So we cannot move ahead here. Let's see here, exact same story. There is B bar and B, which is great, but we cannot take anything common. Now let's see this. So we have D bar, D bar. So if we take it common, we cannot move ahead. What should we do? ChatGPT. All right. There is a trick, and we already went through that in one of the examples. Now, here we have AB, here we have BC, here we have B bar, D bar. So it looks like we have 3 variables distributed in those. Here we have 3 of them, sorry, 4, A, B, C, D. There are 4 terms, 4 literals divided over terms. Here we have 3 of them, and we are missing the 4th one. We are missing the 4th one, which is B. Now we want to add B to this such that we increase the consensus or the commons between those 2 terms or 4 terms. We want to add something to this such that we increase what is common between all those terms. Now, we said what we miss is B. Yes, please. Excellent. Yeah. Yeah. So we said last time we want to add B to this, but you cannot do something like that. You cannot do something like multiply by B. If you do so, you are changing the correctness of the equation. You cannot just simply add literal to a term. But in order to add a B and maintain the correctness, you would multiply it with 1 first. You would multiply only this term with 1. So something like this, right? Now we are not changing the meaning, right? And we know that 1 could be replaced by any of those because both of them equals 1. Since we want to add B to this, so we would use this one, which is B plus B bar. Okay? Is it clear what we did over here? We want to multiply this by B, right? But we cannot do that. For example, if you have this in algebra, 5 plus, again, 3 times 8, can you multiply this by 2? If you do so, you are changing the equation. It will be totally different. You cannot just simply multiply by 2. But you can multiply by 2 over 2 to all of this, and then it will be the same thing, right? That's true. You can do that. Sorry? Yes, we multiply by 1 in order to not changing the value, right? And we replace 1 by anything has B. We could go with this, we could go with that. It's the same thing, right? As long as we have B here, or B and B bar, it's same thing, adding 1. And that will enrich this term with B. Then this term will have for sure something common with any of those terms. Because this one has A, this one has nothing in common with this, right? This one has d bar common with that. In order to have common with all terms, so we said what is missing from here is b. So let's add b. Okay? And then we multiply with this term. And then the entire equation would be AB plus BC plus B bar D bar plus AC bar D bar B plus AC bar D bar D bar. Right? Just multiply B with this plus this with that. Yes, please. That's an excellent point. We recommend you to all the time order them in order to not get confused, because you might miss some patterns when you look at here. Oh, this is maybe D before B, but here B after D, so they are not similar, and get yourself confused with that. So we recommend always to order them in alphabetical order. Okay? So this one, for example, it's recommended to have it as A, B, C, D. So replace, but don't change the not. Okay? So just adding here, you could remove that. We will have it as one recommendation at the end of the lecture. We have some common errors. This is A, B, C, D. Likewise over here. You could do that. Remember, this is B bar, so we would keep it the same. A, B bar, C, D. B, C, B, D. Yeah, it's correct. Okay? Yeah, we recommend that. Yes, please. Oh, sorry. Yeah, this is eating the whole board. I wish like this somewhere else. I'm limited in space, only here or here. All right. Now, what should we do? And you can see the board. What should we do now? AB. Okay, for this one, we can take common with this one, right? So this and this are good. Now with these two, what should we do? Now we have BD, BD, excellent. Then we can cancel something from this together, right? Yeah, AB, AB. And then we have B bar with this. Right? Excellent. Now, let's do it. So I want to take AB common, AB, take parentheses. This is left with 1, right? Now, the other one, we don't want to touch it. Let's take this, AB common. Then we left with C bar, D bar. And now, don't forget this guy, plus BC, right? And now we will take again another common, D bar, D bar. And then we left with 1 from here. And then when we take B bar, D bar, we are left with A, C bar. Okay? Just we took this as common, and then this as common with the other term. Now, whenever we saw something like this, directly factored out to 1. Likewise, over here, 1. And then that would result in AB plus BC plus B bar, D bar. Can we do something? If we take B common here, we'll do nothing. There is another theorem when you saw 3 variables. when you saw 3 variables, right? We call it consensus, I think. Yeah, this one. This one. But this would require 3 variables. Do you remember this theorem? We need one of the variables. So first require 3 variables, right? Second, it requires one of the variables to be, for example, let's assume it x. Then we should have x bar, right? Should have a plus over here. And then take the other 2 variables and distribute them over here. So for example, let's say a, b. And then initiate a third term with the 2 variables that you distributed, which is a, b. If you have this form, based on theorem number 11, we said we could cancel out this guy directly. Okay? But remember, we should have 3 variables first, and then one of the variables should be in one of the term, and then it's not version in another term. And then the third term, we have the other 2 variables multiplied with each other. If we have exactly this structure, then we could apply it and cancel one of them, which is this guy. This should be canceled, and then we left out with this. Do we have this satisfied? First, do we have 3 variables? A, B, C, D, then 4. Then, okay, we may proceed. For example, we could assume 2 variables to be 1 variable, same as we did. For example, assume Z equal BC, for example. So you could assume this. But now let's see if the other conditions are met. Do we have one of those 4 variables in one side and it's not version in another term? For example, let's see those nuts, easy to get. So we have B bar and B, yes. Then we should have somewhere another term to be C, D bar, right? Because here we have X and X bar. Then we have A and B next to them. Then the third term should be directly A and B. A times B. So here we said we want a B and B bar. Then we should have somewhere C, D bar. If we have this, then we could cancel it. But we don't have it as another term, so we cannot proceed with that. So I believe this is the most simplified version of this equation. We cannot proceed further. Okay? All right? Yes, please. All right. So we said we would like to take something in common, right, between multiple terms such that we can simplify further and achieve our goal, which is having something like this, right? Or 1 plus something, which is A or A bar or anything like that, right? We would like to convert this equation into something like that, either this or equivalent forms. For example, 1 plus A bar. All of those are equivalent and would result in 1. Okay? Now, we were trying to take something in common between these two. Didn't work. Because if we take B, we didn't gain anything because it will be B times A plus C. So we cannot move anything further. Okay? Now, we can look at this and this. There's nothing in common. So we cannot do anything about it. Okay, now let's look at this and this. Same story. Cannot do anything about it. Now let's look at this and this. We can say A is common, so take it out. But we left out with B plus C bar D bar. None of those shapes. None of those structures. So we cannot do anything about it. Let's see this, BC, and this, same thing. Let's see this and this. We could take D bar, but same story. We left out none of the structure satisfied, because it will be d bar times b bar plus a c bar. So we are like in dead end, right? We cannot move any further. Like our trick didn't work out here. So to save that, remember we did this in one of the examples before. When we have such situation, you cannot move further, then you could add more literals to any of the terms without affecting the correctness of the equation. For example, we said, what is missing here? We have the A, we have the C, we have the D, but we don't have what is common between three of them, which is B. So our target now to enrich this term with B's. Okay? Now we cannot simply say, let's convert this into A, B, C bar, D bar. We cannot say that. Because now we are changing the equation. We are adding just B. But we can say, multiply this with 1, only this term, not the whole equation. Only multiply this with 1, and it's still the exact same equation, nothing affecting it, right? Because this times 1 is same as this. And we can go ahead from there. If you agree until here, it's very easy to move further. Now we said the 1, we could replace it with any of those three structures, because all of them equals 1, all of them. So we could say 1, remove it, and put this. Remove 1, put this. Remove 1, put this. Any of those structure. But remember, we want B to be added to the term, not A's. So we would change this into, for example, this would be B plus B bar. This would be 1 plus B bar. This would be 1 plus B. So now any of those three you could replace over here and still very correct. We just decided to go ahead with this because we really want the B's. We don't want 1 to be in the equation. And then we decide to go with this one. And now we need to simplify this. We cannot allow, you remember, we're always going with sum of product. This would be our final result. So when we have such situation, we have not A bar, A, C bar, D bar. Those multiply by each other. This is not sum of product. We don't want that. So we decide, okay, let's multiply this with B bar, and this is how we got these two terms. Now this entire thing is sum of product because there are only pluses, and each of those terms are multiplication. So this is sum of product. And then we could move ahead. Now this opens really great door for us. Now we have a proxy such that we can take really things in common between multiple terms, as you all see from over here. Okay? But this was enabled only by enriching one of the terms with things that was common between the three of them, or many of them. Okay? We already took another example around that trick in the past. Any question? Yes.
So the value of the heterogram A, B is actually like
You want to multiply the entire thing with B, for example? Yes, you could do that. You could multiply the entire equation with 1, not with B, with 1. Because if you multiply by B, you are changing the equation. It's like you are multiplying the whole thing here with 2. You cannot do that. You cannot multiply this equation with 2. For example, let's make it clear. You have this in Boolean, this equal x, right? You would multiply these two together and then add it to 5, and this is how you get x. But can you multiply this with 2 without multiplying this with 2? You cannot, right? So you have to multiply both sides with 2, right? Now, it's the same thing as if you multiply this with 2 over 2. You don't need to multiply this with 2 over 2 as well. Because same thing as if you get this 2 over this side, then it will be 2x equal all of this without this 2, right? Now, when you multiply 2 over 2 here, what does it mean? It means you multiply with 1. That's why you didn't change the meaning of the equation. So this is exactly the same as if you multiply the whole thing with 1, and then we replace the 1 with 2 over 2. A, B, and C. Which one?
Okay, no,
Which
it's-
term? Oh, you mean the name of the literal themselves? No, it's up to you. You could use X, W, Y, Z, for example. Not necessarily A, B, C, D. Could be any literal. Okay? Is it clear? Is it clear? All right. Now we are in example number 6. So there is another method to solve it as well. Do you remember theorem number 11? Where we have this guy. Where we have 3 variables, and then one of the variables should be in one term, and it's not virgin in another term. And then the other 2 variables are distributed over the 3 terms, A and B, and then A times B over here. So we could use it to simplify any 2 of the terms. For example, let's choose one of them. So we could, it's up to you which one is X, which one you are considering as X. But remember, that X should exist in another term with a not form. So you could consider B or D bar or C or D because all of them has a not. But now we need to know if they exist in another term without a not. Now, if we consider B not, do we have B somewhere else? Yes, we have B over here. So we can consider these 2 to replace them with this form or this structure. We can consider the D bar. Do we have D somewhere else? No, then we cannot consider D bar as X. Okay, so the first option we have is B bar. Now, what else do we have with a nut? Do we have C bar? Do we have C somewhere else? Yes, we have BC. So C bar, we can consider it as X. What else? D bar didn't work. So we only left with going with B bar or C bar. Now let's go with the first one. When I go with B bar, that means B bar should be in one side, B should be in another term, and then whatever here, this should be plus, and whatever here should be multiplied with each other in the third term. Okay? Now let's see. Where do we have B bar? We have D bar here. Let's use another color, maybe blue. So we have D bar. And what do we have next to the B? It's up to us. Either we choose AB or BC. Let's go with BC, for example. Then we have C over here. And then the third term should be those multiplied with each other. So C, D bar. So we can replace those two things in the middle with these three terms. Okay. Do we have this written somewhere? Yes. This is the question. Now let's move to the table. Yeah, maybe it will be better if I print this table and give you next time. So instead of going back and forth, you can have it all the time handy. Okay. Now we are trying to use theorem number 11. Okay. Theorem number 11 says this is equivalent to this. But we are trying to use the theorem number 11 in different way. Instead of going from this three terms to this two terms, we want to go the opposite. We want to go from those two terms to the three terms. Why we want to do that? Because we try everything possible to take something common, didn't work. So we want to increase the number of terms to increase the repeated things or the duplication such that we can take now more common thing between the terms. So we said, if we want to apply this theorem, it has different requirements. The first thing, it should have three variables. Okay? We should look for three variables. That's one thing. The second thing, one of the variables should exist in both terms, but in one term should be without nut, in the other term with a nut. That's one of the variables. Now the other two variables are just distributed over the three terms. Here's one of them. This is the other one. And over the third terms, we just multiply them together. This is how we get the three variables. Yes? No, this is not related to one. This is the theorem. This is what it says, right? Over here is a theorem. Now, how we get that theorem is another story. So you could build a truth table as we did. So in lecture, I think number 9, we did build a truth table for this theorem. Okay? And we went how we got that theorem out of the other theorems as well. But over here, we are just using it. Now we try to apply this structure or this theorem over the question we have here in blue, right? And we said we only could do that for B or D because they are, no, sorry, B or C. B or C. Because there are only two variables that exist in two terms, and in one of them with a nut, in the other one without nut. So B exists here without nut, exists here with a nut. C exists here without nut, exists here with a nut. So that there are two only options that we can choose to apply this structure for. And if we want to go with B bar or B, then we can replace it with X. Or over here, it's still the same as B. And then the other two variables, we just distribute them over the two terms that we already have. And we have another third term where we multiply the other two variables. And that would give us advantage of replacing those two with those three terms. So our equation would be AB plus these three plus AC bar D bar. So we convert everything over here with this equation. And the only modification we did, we replaced these two terms with three terms based on this theorem. So we replace the two with these three terms. Okay? Now, what did we gain out of that? Did we gain anything over here? Yeah, d bar is common now between these three terms. Okay. So if we take d bar as a common, then we could arrive to the weird theorem. Then we can apply it because we will have something like a plus bd. Or not, let's write it exactly what we will have. So we'll have here d bar, sorry, we are taking d bar common. So we'll have b bar plus c plus ac bar. So you could take those and use the weird theorem in order to go further with more terms. You still remember the weird one? Just c plus anything multiply with each other like x, y. Then you go with c plus x, c plus y. Right? Yes.
For this is that. Or
Which one?
So for the original, so how we use do we have to do it for this? Or want to get
No, you just do it once. If you want to do it twice, it's up to you. You can do it twice. But here we are trying to see our options. Which one would look like similar to this structure? So either we can go with B or C, but we cannot go, for example, with D. Exactly. Excellent. So that's the only option we have. We cannot go with D to replace it with X because we don't have D in one side and D bar in another term. We have only D bar and D bar. We don't have a bar and without bar somewhere else. Likewise with A, we have only A's, A and A. We don't have A and A bar. So we cannot use them to go ahead with this structure. We choose B, you could choose C as well, and then move ahead from there. Okay? Yeah, so this is the first method we use. We explain it here better because we go step by step. We multiply by 1, and then from 1, we go with B plus B bar. And then from there, we multiply this over that, and this is how we get the last two terms, right? It's exactly the same method as in here. And then we could take common from here, common from there, and then we arrive to this. And the second method it's the same thing exactly, but they consider this and this together to get that structure. This and this together, because still we have B on one side, B bar on the other side. Bless you. So if you want to replace those two, let's use another color. Want to replace this and this with our theorem, we have B in one side, B bar on another side, then it means the other two variables should be added as third term. So we have D bar and A, so we just add D bar A. That's our new term that we should add. Okay? Is it clear? Yes. Now you need to take something in common, which is, let's see. So we get rid of this guy, right? So just take AD bar between these two. So if you take AD bar, we left out with C bar plus 1. Anything added to 1 is 1. C bar plus 1 is 1. So this is how you cancel out this guy, and you move ahead from there. Okay. Over here, we cannot do that. We cannot take common because here we don't have CD bar, not C bar, D bar. But can we do something else? There is D bar. There is A over here. Yeah, we cannot take common from here, but we can move ahead with the weird theorem over there. So this is a third method. You can consider it. And we have over here another 2 ways to solve it. Okay? Sorry? What is? Exactly. Excellent. What is the point of having this simplification in order to deal with computer architecture? That's a great question, actually. Now, remember, all those equations will be processed where? The CPU, right? So we're going to have the processor, or ALU, performing all those operations, right? Now, last time, we discussed an example of a gate or logic gates. And when we simplified them, we really slashed the number of logic gates by half by just simplifying the circuit. For example, you can look here. How many AND gate, how many OR gate, how many NOT gates over there? Let's see, let's count them together. Maybe we can use the other side. So let's see, we have AND, we have OR, we have NOT. Let's quantify them. How many AND do we have? So there's 1, 2, 3, 4, 5. Assuming this is 2 input. Okay. How many OR? 1, 2, 3. How many NOT? 1, 2, 3, 4. All right, perfect. Now this is the original. Let's go with the simplified. Now this is the simplified, or this one. Both of them are the same. How many AND? 1, 2, 3. How many OR? 1, 2. How many NOT? 2. So we almost cut by half or 2 times all the logic gates. Now this is what it's telling us. It's telling us if you convert this logic gates into assembly code, and each assembly line you need to perform just 5 operation of AND, 3 operation of OR, 4 operation of NOT. That's in total 7, 5, 12, right? 4, 3, 7. So here you need 12 assembly instruction, right? And over here you need 7 assembly instruction. So this would take 12 cycles the processor to be executed, and this would need only 7 cycles to be executed. That means a program written using this equation would take half of the time to be executed compared to the original equation. Right? Now, who's doing that simplification for me? There's a lot of like very bad developers just draw those mathematical equation, but then all of them get optimized to the same thing. And who is doing that? The compiler. When you compile your program, the compiler, depending on some flags, for example, if you are compiling C++, there is a flag called O1, O2, O3, O4, and so on. This means I want optimization level 1, optimization level 2, optimization level 3. If you specify that, if you program C or C++, you will see this thing in the command line when you compile the program. So if you add any of those flags when you compile, when you run your program, then that will tell the compiler, I want the best optimization ever. Then the compiler try to optimize every instruction over there into something better form or cheaper to be executed. So the compiler will convert this for you into that. How we'll do that? Using any of those theorem or simplification. But I might trick you for now that those compiler are using those theorem for simplification. In fact, they are not using that. The compilers are not using the theorem for the simplification. In a week or so, we will take a much better way to simplify an equation without any confusion. A very nice way using just tables. Yes. All right, that's extremely excellent point. Why we go to the basics if we have very simple way to solve? That's a very logical question, right? Now, how you would know how another scientist came up with a very nice way to solve without going through this path? And you will see this extremely needed if you go for grad studies or for companies, exact same story. How you would solve a problem given to you and you are the first to solve it. How you would solve it, right? You need really to go the difficult path. You need to deeply think, what is the pattern? Now I have a lot of equations. I need to simplify them. Every time I'm trying to simplify, I'm trying to build my own algorithm. So first time we said we want to look for these guys, right? So this, you could build a compiler that would be looking for this pattern at the beginning in order to simplify. But then your program might fail, as in this case, for example. We couldn't move ahead with any of this structure. Then your program will have another if condition. If you have a variables distributed over multiple terms, but one of the terms is missing those literal, then you would add it to that term, for example, right? This is how we build the compiler. So we have a lot of if, else, if, else, if, else. And then you could come up with a simplified form of all of those if, else, because we already know all possible options, right? And this is how you come up with a much nicer way to solve any problem. You'll see this in many cases when you do research for master or for PhD studies, okay? You're always coming through problem that nobody solved before. This is how you get a degree. You need really to do novel contribution. You really need to do something new. And to do that, you cannot simply just sleep and wake up and that's, oh, I come up with an idea. You have to really suffer for days, weeks, months over the same problem, keep thinking about it even while taking shower. And then you'll see that you'll see some optimization happening over there and there. Okay? But sometimes using those theorem is way faster than the other method. The other method is systematic. You don't really need to think about it. You just do something, some tables we call, right? And do something with it, and then you will come up with the simplified version. Okay? It's very systematic. Step 1, step 2, 3, 4, 5, done. Over here, there is no systematic way. The only way you need to practice, right? But sometimes this is way faster than the other way. So that's why that is not replacing this. This is not replacing that. But the other one, you could use it all the time, will never fail. This one, you need to suffer a bit sometimes. Some questions, it's really tricky. Okay? Those are really great questions. Yeah, for this slide, this is exactly what we discussed. Your classmate asked, can we order them? Yes, we recommend that all the time. Please order these terms. This ordering is not a must, okay? But we require it in order to not forget whether this is similar to this or not. For example, if you have in any of the terms, like BC plus CB bar. Now you could look here, oh, it's confusing. There is BC, but here you have CB. It's exactly the same thing as BC plus B bar C, right? So we recommend to have it this way. In this way, you can see, oh, it's perfect because we have common C. Take it out, and then you have B and B bar, right? Although they are the same thing, but you might get confused just because the ordering here does not match with this. So you might get blind or blurry and not seeing the C, and then you could ignore it, especially if there is something in the middle, like other term, like AD, for example, or AB or A something. Okay? So I recommend you really to sort these alphabetical order. Now let's go with another example. Yes. B, where exactly? Which line? There are 4 lines. Third line. No, they are exactly the same, but this is what we are saying. Please go with the order. So alphabetical order, B comes before C, right? So we prefer this way over this way. But they are exactly the same thing. Both of them are correct. Here it says incorrect, but that in a sense of that sentence. But if you have it in the exam or any of the question, it's perfectly correct. Nobody can deduct any grade, okay? It's just a way to give you a better clarity for how you solve the question. This one is extremely easy. It's very similar to what we just discussed, right? We have 2 things multiply with each other. Then this directly telling us there is something related to the weird theorem, right? Because remember, I think we are done from this side. You remember again, what's the weird theorem? So we said A plus BD, for example, or BC. Then it's equals not sure if she can see. A plus B, A plus C, right? Zihan, can you see the slide? Can you see the board? Yeah. So whenever we saw something similar to this, so that's the first requirement. The second requirement, one of the variables should be in both sides, which is A in this case. Do we have such structure over here? What is it? We have A, right? Distributed in both of them, bless you. So we can take it out with the plus, and then everything else, we just multiply, right? Straightforward. For example, A plus, we'll take it common. And then we left with anything multiply with each other, which is BC times DE, which is A plus BC, or let's sort it. B, C, D, E. Right? Now, what should we do about it? Sorry? Excellent. Why? Because this is already sum of products, right? So this is 2 terms. There is sum, and each term is a product. There's no sum inside. Okay? Now, someone could go with the difficult way, the hard way. It's correct. Nobody can argue about it, which is just as you would solve Boolean equation, would multiply this with this, multiply this with that, and then plus this with this with that. You could do that as well, right? Same as you do in Boolean algebra, okay? Which is, yeah, I hate this. I hate this. We should have, I think in one of the classroom in Switzerland, they have the exact same situation, and then we order a board that's portable, that you can move around. I think that would solve the problem. I may ask for that. Yeah, so it will be A times A plus ADE plus ABC plus BCDE. Right? Then this one would result in A, not 1, right? Remember, not 1. So this is 1, sorry, A. Then we can take A common from here, for example, and then you can proceed. Can we simplify? Yes. This, for example, BC, can take it common. There is DE, can take common. A, you can take common between all of those. So let's take A common. A, 1, amazing. Whenever you saw 1, that will save your life. 1 plus DE plus BC plus BCDE. When you saw 1, add it to anything, directly cancel it. You add arrow like that, and you say 1, then 1 times A, it's A plus BCDE. Yes. Yes. Because AA, we convert to A, and then you take A as common, then you're left out with 1 plus stuff. We said last time, I think in example 3, we saw A, right? Triple A's. Same thing. All would result in A, not 1. All would result in A. Doesn't matter how many A's we have. I think Jeremy asked that question. We have 4 or 5, exact same thing. All would result in 1 A. Okay. Let's see. Yeah, the trick here, you can see there is a pattern. It's really not random. There is really, if I saw this, then I should use this method. If I saw this, then that's the right theorem to be used, right? And the only way to get that sense is to go over multiple examples, as you can see from here. Once we saw this form, remember, this is, you still remember the picture? I'm going to move the slide. Just capture it in your mind. We have 2 parentheses multiplied with each other. This is exactly the same as this. Don't get confused with the large number of literals added to each other. It's exactly the same thing. The trick is to have one of the literals in both sides. That's a requirement here, which is A here, and then we can easily get it out, A and plus, and then everything else left out, you just multiply with each other, like in here. Here we left with B and C, just multiply them together. Here we left with C plus D plus E and B, so multiply B with all these 3 terms, as in here. Over that question, we did the exact same thing in here. We took A as common, A and the plus as common, and then whatever left, just multiply it with each other. That's the pattern. So this is how we build a compiler. Whenever we saw this is the input, do this with the output. Okay? Any question? Now we have the 2 methods we discussed over here. Right? Okay. Do you still remember this story? The guy going to the restaurant and want to eat only if the restaurant was clean or no certain meal was serviced, right? Exact same thing in here. And we said any question could be solved as sum of product or product of sums. The only thing we said, as a matter of fact, that we should look at the output, and depending on the number of ones and number of zeros, we can choose which one over the other. Okay? For example, here, sum of products, we said if we have less number of ones, it's always preferred to go with the first method. If we have less number of zeros, always go with the second method. Okay? In order to get less number of terms, such that you can get optimized equation right away. You don't have to suffer, and you can see that from the equation we built. This is one term, this is 3 terms. So if you go with this method, then you will suffer a lot trying to optimize this one. But if you go with the first one, it's directly optimized. Now, this is exactly the same as this. Do you believe it? How? How we can simplify it? C plus common, which is this and this, right? The first two, C is common. Excellent. Excellent. I wish I have some bars today. I don't have bars today. What's your name? Richard? Richmond. Excellent point. So the first two, we have something in common, and this is similar to the weird form, right? So C plus, and then whatever left, just multiply with each other, which is M and M bar, right? This is the first one. And the second is C bar plus M bar. Thank you. Now, whenever we saw this, cool. What does it mean? Anything multiply with its own nut would result always with 1. Are you sure? 1 times 0, it's same as 0 times 1. And would always result in 0. This is algebra, no magic, right? Now, M could be 1, this situation, or it could be 0. We have this situation, so it's always 0 in both cases. Then directly, this would result in 0. Anything added to 0, it's that thing, right? So this would result in C times C bar plus M bar. Now what you should do? Multiply, right? Or distribute C to here, C to there. So that would be C bar plus C M bar. Can you see, guys, this side? How we should move next? Excellent. Same story as in here. So this one, 0. 0 plus C M bar. And this would result in C M bar. Exact same thing. But you really could avoid all of that stuff by just going with the first method, because it's less number of ones in the output, right? So that's telling us you could solve all those simplification as a form of product of sum or sum of product. Until now, everything we solved was sum of product. So there are many terms. Each term has a multiplication inside it. There is no sum inside any term. And all terms are added to each other. That's why we call it sum of product, right? And that's the most simplified way you could arrive to the equation. But you could also keep it as a product of sum, as you can see in here. And the final answer will be also product of sum. I have 2 examples here. Is this sum of product or product of sum? First, you need to decide where are the terms. Where are the terms? Where are the terms here? A is one of them. and this guy is another term, right? Now, do you have an summation or add sign in any of the terms? In the term itself? No. What do we have? What sign we have in each of the terms? This, no, nothing, right? In this term. How about this? Multiplication, right? So that's why we call it sum of product. Sum of product, because we are adding things that are multiplied with each other. Sum of products. Okay. Now the question asks you to convert into product of sum. You like De Morgan theorem? Yeah, De Morgan sometimes doing the magic. Sometimes really a nice way to convert, because you know De Morgan will flip this sign, but will not flip the things in here. So will not convert those into sums. So do you remember the weird theorem? You can go with that. So please go over this alone at home. This and the next example is exactly the same. I think we are fed up with the weird theorem. We went through it a million times. You have the same story over here. Please go it in your own. Okay. And now I think we should be fair with this guy, the De Morgan. We didn't take an example on De Morgan. Okay. So we should really take some examples before we wrap up. Still, if you have any question with the previous two examples, please ask next time after the class directly. I can stay here. Normally I stay for 15 minutes. There are a lot of questions I get from your colleague. All right. Let's go with the fun. De Morgan. Remember, De Morgan, you should have a nut somewhere over multiple things. If you don't have it, as Alex said last time, you can add just 2 bars. That will maintain the correctness. This is correct. It's same as you said, a nut. You remember this from the trivials? Adding 2 nuts would result in having the variable or literal without any nut, right? So if you don't have that and you want to use De Morgan, just add those 2 together, okay? Now here it's already added. So let's see. The only trick in De Morgan is to decide where are the 2 sides you want to distribute that nut over, okay? So when you have a large nut like that, how many literal you have? 4. I want to distribute that nut over these 4. What should I do? You always want to decide where are the 2 sides. You should decide I wanted 2 sides. Either can be this split, this one side, this is another side, or you can split over here, or you can split over there. Why this is important? Because this is going to flip the sign between the 2 sides. For example, if you have B, C, D, E, all with a nut. Now, if I decide that this is the separator, remember there's a nut here. Sorry, there is a dot here. There's a dot here. There's a dot there. If I decide that this will be one side, this is the other side, then it will be B, C, all with a nut. And now I'm flipping this sign into plus, and this another side, D, E, all with nut. Because I decided that those are the 2 sides. If I decided that this will be one side and all of that another side, then this would be B, C, D plus E. Now the nut is distributed over there. Yes, please. Yes, of course. Of course. You can go further with this guy, for example. This guy would result in, again, choose the 2 sides. Where do you want your 2 sides? That's the only thing in De Morgan. Just decide where are the two sides and move ahead. For this guy, where are the two sides? I want to split them from here, for example. So I will have B in one side with a nut. This sign, whatever over there, just flip it. If it is multiplication, make it addition. If it is addition, multiplication. This is multiplication, so it will be add, and then CD as one side. So all of it with the same nut. Don't dispute the nut yet. And don't forget this guy. So we have plus E bar. I could go further with this because we still see a nut distributed over multiple literal. So this would result in B bar plus. Now, this is easy because you have no other option. This will be one side. This is another side. Done. So C bar. Remember, there is multiplication over here. So it will be plus D bar plus E bar. That's De Morgan. Not yet? I lost you? Anna? Yeah, it's not. We are explaining how we go with De Morgan. Now let's go with the equation. Okay. All right. Yeah, Hannah. Go ahead. Go ahead. You have a whole nut at the top of the entire thing, right? Want to distribute it further. So you should split into two sides. Decide for me. Where do you want those two sides? Now, remember, there are some cumbersome on there. There are multiplication and addition and stuff like that. Excellent, perfect, excellent. So we want to take everything within the parentheses as one side, everything else as another side, okay? What do they have in between? No, there is a parenthesis, right? Everything in there. And there's the other side over here. What they have in between? Multiplication. There's a multiplication over there, right? Okay, so the first side, which is A plus, just keep it intact. Don't touch it. B, D. The bar is also over both of them. So keep it as is. That is one side. The other side, also keep it as is. Don't change. So this one side, this is another side. Now, De Morgan is telling you that the nut at the top divided over both sides. So we'll add a nut over here, and a nut over the entire side. And then whatever sign in between, just flip it. Over there we have multiplication, then that will be a plus. Okay, that's De Morgan. The only trick is to decide where are the two sides. That's the only thing you should worry about. Everything else is exactly the same. Doesn't matter if this is multiplication or add, just flip it to the opposite. Now, again, this is trivial, nothing to do about. When you have two nuts, they cancel each other. So this would result in C plus. Yes, Hannah, go ahead. Now we have a whole nut over many things. Decide where are the two sides. Excellent. So we wanted this one side, this is the other side. So now write those two sides, right, as they are. Don't change anything. This is one side, other side. Now what is the sign between? No, this one. What is it? Plus. Yes, change it into multiplication. Now, if there is a plus over here, so it would be good if you add parentheses over here, same as in Boolean, to not get confused, right? But now, since all of them multiplication, doesn't matter. If you add it or not, it's the same thing. Okay? Now, we are not done yet. Hannah. So we had the nut. We flipped the sign, but we didn't distribute it. You need to distribute the nut over there. So here we have a nut, and here we have another nut. We need to split this guy at the top. We split it into two, and we flip the sign. Okay, this one is same thing. Nothing changed. Now, this one is the trivial. Two nuts cancel each other, so we left with BD. And this one, A bar. Is this sum of product or product of sum? If you are ever confused, check this. Check this. These are the terms. Do we have a plus in them? No. So these are products. And then there is a sum in between. That's why we call it sum of products. Okay? Is it clear for De Morgan? It's the easiest, the sweetest theorem that you could have. Nothing magic about it. The only difficult part is to decide where are the two sides. Okay? Let's take another example. I need someone else. Any volunteer? No, you already did. Who's else? Okay, go ahead. First, we need to decide where are the two sides. Let's see. Yes. So you want everything with the parentheses as one side, everything else as another side. Okay. So let's repeat it over here. All of them done. So A, C, whole nut, E, plus D bar. This is one side. The other side is just B. Now what is in between? Multiplication. Excellent. This is one thing. Now the nut at the top. What do we do with it? Split it over here and everything. So if you choose this as one side, the nut should be the entire side. And then, now this is as is. Don't do anything about it. This one is still. So we have a whole nut. Where are the two sides? This one. Why not over here? Can you split this? Can you split this? Can you split this? Why?
It'll make it more complicated.
And it's wrong. Because Boolean, the multiplication has much better priority than addition, right? Then, okay, perfect. So this will be one side, the other side. A, C, bar, E. The other side is D bar. Don't forget everything we had. Yeah, don't forget that. And we're still not done here. What is the sign? Multiplication. We're still not done. What do we do with this? And remember, this is one side, so the nut will be over the entire thing. Now, this is trivial. Excellent. D. And then we still have the other guy. Please don't forget. Most of the people or students will forget about everything else. They keep focusing on things to simplify and keep forgetting everything else. Okay? Now in here, what should we do? So we have the multiplication, and then with this guy, what should we do? Here, there are multiplications, so it doesn't matter. So you could take any of, but remember, there is a nut distributed over A and C together. So you cannot split A on one side and everything else on another side, because there is a nut on top of them. It's like parentheses over this and this. So A, C, and there is a nut on top of it. Don't forget that. And then E in another side. So just keep a space between them. And now, what is the sign there? Excellent. We are not done yet. Not over here and not over there, right? And then there is a parenthesis over here. Now, two knots, we'll cancel them out. And then we left with AC plus E. There is a multiplication over here. So that would result in D. And then there is all with B bar. Now, what should we do? Are we done? Are we done? No, we don't have not. The not over E and B. Which one? Oh, excellent. Excellent. This one multiply over here. Right? So you maintain that. And now this is wrong. Okay, so we remove the two knots, AC plus this, multiply by D, multiply by B. You could multiply this with this, and then you distribute over this plus this, right? So it will be AC. Let's sort alphabetically. Then this will be B bar, D, plus B bar, D, E bar. Okay. Is this sum of products or product of sum? These are the terms. Do we have any plus in them? No. All multiplication. So those we call them products. This is sum, so we call it sum of products. Okay. Let's see. Yeah, it's exactly the same, right? Oh, why we didn't sort this? I thought I was sorting. Oh yeah, A, B bar, C. Remember, this sorting is just to make the things more organized, but you can do whatever you want. All right? Is it clear with De Morgan? Based on everything you saw so far, all the examples, there is a list of things that you should not do. Please go over it. Go over it. You'll see it really makes sense. It's really making sense. For example, applying multiple theorems together. Don't ever do that. It's really wrong. Don't feel like, oh, you are super good in this. Apply one over another. Apply one, get the final equation, then move it next with the next theorem. Don't apply your own theorem, okay? Don't invent. Make sure what each theorem requires, what are the requirements, make sure they are there, and then move ahead with that theorem, okay? And hopefully I was clear whenever I stated any theorem, I told you what are those requirements and whether they met or not, okay? So make sure you add your own notes on the table of the theorem and add those requirements to each of them, okay? You'll see something like this we visited hundreds of times. For example, I think Hannah got confused with that, and she said like A times A bar is 1, right? If you're ever confused or you're not sure, just replace it with truth table right away. If this is 1, if this is 0, what will be the final output? So those are wrong, those are correct. I don't know who would say this equals to B, but we got all those situations in the exams. Yes, please. Yeah. So this one has a single nut, right? So you cannot do anything about it. You cannot apply De Morgan here. because you cannot split this over two things. There's only one side. So now with this one, yes, there is a whole nut on the entire thing. So you can start from here, right? Now with this one, in order to distribute it in two things, you need to decide where are those two things. But remember the Boolean equation. In Boolean equation, there are multiplication over here. There is a sum. And this you can consider as whole between parentheses, even if I'm not having that in the question. But this is what you can consider over here. So the only way to split this is over here, right? And then you can move further and try to split further and further, okay? If you didn't split this, remember this nut is over A and C only. It's not over the entire thing. So they are not canceling each other. So now you have a whole nut over three of them, and you have one nut over two of them. So you cannot leave it as that. Okay? You have really to go further and try to split this into two sides, and then this one will cancel out. You got the nut over here and so on. Over here, you cannot do any further. So there is no nut over many things. If you get nut over C and D, you need to go further. Don't stop here. This is not complete answer. If there is a nut over here, this is I added myself now. So if there is a nut over here, you need to break down this into C plus D, and then the nut distributed. But remember, this is part of this part. So there's a nut, and then there is A, B bar. All of this as one term. And then you have B bar, D, E bar. So this one side, this is another side. Please maintain those parentheses, because it's going to change the answer. Okay? Because this whole thing was one term, and you would maintain that as one term. And this, there was a multiplication over here, multiplication, multiplication. So that's why we add this in all parentheses to maintain that multiplication over here. Okay? Again, this is with the assumption that we have a bar over C and D. So we are changing the question over here. Right? All right, guys. Please go over this list. This is extremely important. I cannot explain it to you because we went through all of that. The only way, you just go and try to remember or see if it makes making sense or not. Okay? Thank you so much. We'll see you next week.